Okay, so I said that I would get the video up this evening, but I had a little bit of time now, so I wanted to get the video up as early as possible per some of your requests so that you can start studying for our next quiz. The quiz is going to be on Tuesday. It is 50 questions, all multiple choice. It's going to be on chapters 36 in Bouchon and chapter 4 in Carter and Veal. So I'm hoping that this test is more review than anything else for you. But I do want to point out chapter 36 is a lot of memorization, a lot of numbers you need to know. So I want to make sure that you prepare, maybe make some charts or something for yourself so that you can remember it. And then chapter 4 in Carter and Veal, it's equipment that you work with every day, and it's probably a little bit of review as far as grids are concerned. So hopefully that section will be a little bit easier for you. So I'm going to start with chapter 36. Let me just start my slideshow and get my lovely pointer. I think I'm going to try the highlighter this time. Okay, so designing for radiation protection, chapter 36. Some key points I want you to remember, and we have talked about this before, but when we're talking about the minimum amount of lead in the aprons that we use, we want to remember that it is 0.5 millimeters of lead. That's the most important. We still do need to eventually know the gloves and the wraparound, but for our general aprons, that's 0.5 millimeters of lead to protect us from the radiation that we're receiving. The next thing I wanted to point out, and we've had this question before, but I want to kind of keep bringing it back to the forefront, is the amount of tube leakage that is allowed from our X-ray tubes. It cannot exceed 1 milli air kerma per hour or 100 milli Rankine per hour at 1 meter from the source or from the actual tube itself. So if a person is standing 1 meter away from the X-ray tube, if they put a Geiger meter there, it cannot exceed 1 milli air kerma per hour or 100 milli Rankine per hour. Make sure you know both because you never know which way it's going to be asked. A couple weeks ago, I had lectured on chapter 36, and one of the things I had said was the control panel has certain indicators on it that are important for us as technologists. And the most important thing with the control panel is that it indicates that the beam is on. So every time the beam is on, we can have two separate types of indicators. You can have a visible indicator, and then you can have an audible indicator. The visible one is that amber light that shows up when we take the exposure. You can either see it on your portable machine or you can see it on the console itself. And then the audible, where we hear the little beep, that will also indicate that we have taken an exposure, and that is an NRC guideline. It has to do that. Here comes the numbers that you need to know. So like I said, I think the best way to do it would be to make a chart to remember everything, or find a partner and just quiz each other back and forth, or flashcards, whatever works for you. But with SID, this is important. The SID indicator needs to be within 2% of the indicated SID. So if my X-ray tube housing said that I was at 40 inches, then the actual SID needs to be within 2% of that 40 inches that I've seen. The collimator has to be within this is terrible highlight, sorry guys, within 2% of the SID. So when we collimate down, it has to be within 2% of the SID. So we're running a theme here, 2%, 2%. Next one, the PBL. If you don't remember what the PBL stands for, it stands for positive beam limitation. And what the PBL does is when we're selecting on our tube housing the size image receptor we want to use, whether it be a 14 by 17, 10 by 12, 8 by 10, the PBL will automatically collimate the light field down to the size image receptor you have chosen. It's a safety mechanism. That too has to be within 2% of the SID. So now we've got 2% PBL, 2% collimator light, and then we've got the
2% for your SID as well.
Okay, so SID 2%, collimator 2%, PBL 2%. All right, that's pretty easy.
Now we're going to go on to total filtration.
Now, I think probably last year, and even we talked about it again this year, that the total filtration deals with the filtration inherent in our X-ray tube housing and whatever we add to it. So at 70 kVp, the total filtration must be 2.5 millimeters of aluminum. And the reason why we refer to the 70 kVp filtration most often is because that is the average kVp that we use in radiology departments. If we're using lower ranges of kVp, then of course the filtration would be less, and if we're using more kVp on average, then obviously the filtration would need to be more. And that is the total filtration, so that's the added plus the inherent.
I had also talked about some
quality assurance tests that we need to do, and the two most often performed in radiology is reproducibility and linearity. For reproducibility, it is exactly what it sounds like. If you are able to reproduce the same intensity for a given exposure every time, so if I use 70 kVp at 30 MAS and I got 3 milligrays, and then I did 70 kVp at 30 MAS, a few minutes later, I should still get 3 milligrays, and so on and so forth. So it's being able to reproduce the same intensity using the same technique over and over again. And that variation cannot exceed 5%. Moving on to linearity, when we talk about linearity, that means it's going up in a line. So when we talk about linearity, we're referring to two adjacent MA stations. So if we use the 50 MA station and the 100 MA station, or the 100 MA station and the 150 MA station, they just have to be stations next to each other or adjacent, and then we combine them with a specific exposure time. The intensity has to be able to go up proportional as you go up in each MA station, and that variability cannot exceed 10%. So reproducibility deals with reproducing the same intensity with the same technique. Linearity deals with reproducing the same intensity at varying techniques as you go up in your MA stations. So reproducibility is at 5%, linearity is now at 10%.
Here's a little breakdown of everything together. So total filtration at 70 kVp, 2.5 millimeters of aluminum.
Collimation has to be within 2% of the SID. SID indicator has to be within 2%. The control panel must show your beam on time.
The tube housing cannot exceed 100
millirankins at 1 meter or 1 milli air kerma. Your PBL has to be within 2%. Reproducibility within 5%. Your linearity, ooh, I lost my thingy. Linearity within 10%.
And then we're just going to totally kind of
ignore these guys down here. So don't pay attention to this stuff, okay? All right, next slide. We're going to start talking a little bit about fluoro. And fluoro, we get a lot of exposure. That's our highest area of exposure as X-ray techs. What we need to remember with fluoro is that in order for an exposure to be made, the switch has to be depressed with force. So it's considered a dead man switch, meaning you have to physically put pressure on it in order for it to give an exposure. Super important for fluoro. We have to make sure that we keep proper SIDs so we don't cause skin burns to our patients. So with fluoro, we have two different types of machines. We have a mobile unit, which would be our C-arms, or we have stationary units, which are the units that we go into the rooms and do esophograms or upper GIs. And each of them have specific SIDs, or SSDs, I should say, source to skin distances, that we must abide by. We cannot make the distance any shorter because then we will cause skin burns. So for a mobile unit, it cannot be less than 30 centimeters. And then for a stationary unit, it cannot be less than that 38 centimeters. So mobile is 30 and stationary is 38. We also have to be certain that the exposure that we are giving the patient isn't going to cause a sentinel event. So we have to make sure that the tabletop fluoro should not exceed 2.1 Rankine per minute or 21 milliarkermas per minute. So whenever we're talking about Rankines, its equivalent SI unit is an airkerma. When we're talking about rads, then we're going to be talking about grays. So whenever you think of Rankine, that goes with the airkerma. The filtration, again, is 2.5 millimeters of aluminum at 70 kVp because that's the average kVp that we use in most radiology departments. Something to remember with fluoro is that we have some protectors that help us out. One of them is that Bucky slot cover that's on the bottom by the table, and it comes up and basically protects whoever's standing next to the fluoro machine from getting exposed since the source is coming from the bottom. And those Bucky slot covers need to have 0.25 millimeters of lead equivalent in order to properly protect the person that's standing next to it. So your Bucky slot cover is 0.25 millimeters of lead equivalent.
We also have the protective curtain, and that's that curtain of lead
that is hung around the fluoro tube housing. That also must be 0.25 millimeters of lead equivalent to provide the proper protection for the patient or the person standing next to the machine. Also with fluoro, in the OR and in regular cases, we have that timer that goes off. It's a cumulative timer, meaning at every 5 minutes, it's going to start to go off. And what it does is it alerts either yourself, the technologist, or the doctor to let them know that they have hit 5 minutes of fluoro time. It does not terminate the exposure. It doesn't start an exposure. It doesn't pause the exposure. It just is an audible alert saying that they've done 5 minutes and maybe they should think about closing up the case. So cumulative timer is up to 5 minutes, and it's just an audible alert. It doesn't stop the machine. If you were still awake during my lecture on Chapter 36, I did speak about the dose area product, or the DAP, D-A-P. The DAP is a quantity that gives us an idea of how much a specific volume or amount of tissue was irradiated. It gives us that dose. So if we're in fluoro and we're maybe doing an upper GI series, the DAP will tell us how much fluoro the area between the mouth and the duodenum got exposed and how much radiation it had received. So that's your dose area product, meaning the dose to an area. So if you think about it that way, it's a volume of tissue and the dose that that volume of tissue has received. That's it for chapter, wait, no, I lied. Shh, I lied. Nobody listen, because this is still at 36. Okay, but there are just a couple more things I want to talk to you about. Types of radiation. There is primary radiation and secondary radiation. Primary radiation, we're just talking about the actual beam itself, or the useful beam. That's the primary beam, primary radiation. And then there's secondary radiation. And secondary radiation is generally the scatter and the leakage from the X-ray tube. So that 100 millirankine per hour at 1 meter, that tube leakage, that is considered secondary radiation because it's not the actual beam. And because we need to differentiate between primary and secondary radiation, we have to think about primary and secondary barriers to protect ourselves and the public or fellow patients or coworkers from being exposed to radiation. So primary barriers are anything that's exposed to the primary beam. So when we go into an x-ray room and we take a look at the chest unit, the wall behind the chest unit is considered a primary barrier because the x-ray beam is constantly being pointed in its direction. But the wall that is where our control panel is, or the console, we're really not supposed to shoot the x-ray beam in that direction. So that is not considered a primary barrier, it's considered a secondary barrier because that barrier needs to protect the technologist from tube leakage and from scatter. The big thing I wanted to address for this coming test is specifically scatter radiation and what or how much of it is accumulated at 1 meter from the patient. So with scatter radiation, the intensity of scatter radiation is approximately 1% of the useful beam at 1 meter from the patient. So just like when our tube leakage is 100 milliroentgen per hour at 1 meter, the intensity of that scatter that comes off of our patient, that is going to be 0.1% of what the useful beam is, or the primary radiation is, at 1 meter. We've discussed before dosimeters or dose meters. They're monitoring our doses, and as far as dosimeters are concerned, we generally use these film badges here. They're the cheapest, easiest to work with. We have to turn them in hopefully every 30 days. It doesn't always happen that way, but we do use them for our own monitoring. Then there's optically stimulated dosimetry and thermoluminescent dosimetry. Both of these are more sensitive, meaning they can detect smaller quantities of radiation than the film, but the one that I also want to point out for this particular test is the thermoluminescent dosimeter. The thermoluminescent dosimeter is usually used to detect patient dose, or that DAP that I talked about during fluoro, because it is more sensitive to lower levels of radiation. And dosimetrists like to use it because they're very small, portable, easy to use, and their readout provides us the tissue dose. So that volume of tissue that's been irradiated, that's what the thermoluminescent dosimeter provides to us. So we're able to see the DAP for the patient. The only problem with the thermoluminescent dosimeter is it's not an immediate read. So we would still have to process the badge in order to see what the actual read was. So it takes a little bit of time. It's not instant gratification. Now that's it for Chapter 36. So again, lots and lots of numbers. Please make sure you remember them. They're not going to be trick questions. You just have to remember the numbers and what they're associated with. So now moving on to Carter and Veal, Chapter 4, that's your photostimulable phosphor plates, or your PSPs. These you work with on the floors, that's your CR systems. They are cassettes. They look a lot like what we used to use with film screen. They are very light, durable, they have aluminum backing, they have some anti-static felt in them to help with static and dust buildup and things like that. They can be reused over and over again, whereas film, you had to use one film, process it, and send it on its way. These can be reused several times until they wear out. So there are definitely some advantages to using the PSPs versus film, but all the equipment is the same. So the equipment never changes. The same equipment that we used to use with film, we can certainly still use with the PSP system. I know everybody was studying for their positioning test, so hopefully you sort of paid attention to when I was talking about the layers of the imaging plate being like a sandwich. You do need to know all the layers of the plate and what their purposes are, okay? So the first layer, obviously, the protective layer, what do we think it's going to do? Well, it's certainly going to protect. It's going to protect everything that's in between the two major outer layers of the cassette. Then you've got your phosphor layer, which is all right here. So this phosphor layer is where your photostimulable phosphors are. And our photostimulable phosphors come from that barium fluorohalide family. Again, those photostimulable phosphors come from the barium fluorohalide family. And what those phosphors do is when they're stimulated by light, those electrons get excited and bombard each other and start to emit light themselves because they're photostimulable. Once they emit light, it gets hit in this reflective layer, which is right here. And that reflective layer pushes the light forward. So it moves it forward. Like anything would reflect, it's bringing it forward, okay? This conductive layer is going to stop some of the static buildup that occurs. And your support layer obviously supports all of these other layers. And then you've got your backing. And your backing is usually like a plastic or an aluminum. This light shielding layer here before the backing is an aluminum backing. And that basically stops any of the scatter and absorbs any scatter that's coming off of the phosphors that have been stimulated. Then you've got your backing, and then you've got your barcode reader. And our barcode reader, we've all done this on the floors. We scan the barcode reader to go with the patient. So it's basically for patient identification purposes. And I pretty much already told you all of this, but just so that you have it in written form, the protective layer obviously protects. The phosphor layer is also called the active layer. So that's where all the magic happens in that phosphor layer. So it's also considered the active layer. That's where all of your electrons are going to get trapped after exposure in that phosphor center, I guess is what it's called. That's where they get trapped, and that's where that image is going to be stored. And then, of course, like I said, the most common are from the barium fluorohalide family. I did talk to you in class about the dyes, and some of the dyes help absorb the spreading of the light so that you don't get image blur. Not all cassettes have the dye, though. Your reflective layer, the big thing to remember is that it sends light forward, and then your conductive layer reduces static electricity. The color layer, I didn't talk too much about in class, but some of the newer plates contain the color layer. It's usually between the active layer and the support layer. And what it does is it also absorbs the light and reflects like emitted light. So it absorbs the stimulating light. So the stimulating light coming in, that's stimulating the phosphors, and then it reflects the emitted light coming from the phosphors. That is it almost kind of works like the dye works. Support layer just supports everything, and the backing obviously helps protect the back of the plate. So when an image is taken from the remnant beam that passes through the patient, it interacts, those photons interact with the electrons in the barium fluorohalide phosphors, and then it gets stuck in that phosphor layer or phosphor center and traps it in there until it is exposed by the reader and until the signal is turned into a digital signal. It can be trapped for several hours, but it starts to degrade almost immediately. And then, of course, there is always going to be a residual left over. Even if we erase the cassettes, all of the energy cannot truly be gone. There are a few different types of readers. We usually use the line scan readers. Depending on the manufacturer, you can have a point scan reader, but the most common one is the line scan. I know some of you had said that you do have this specific reader. I've seen a few different types of readers in my travels, so it's just all what you're used to working with. The readers have the helium neon gas lasers that stimulate the electrons that have been trapped in that phosphor center, and it causes those electrons to get excited and emit light. That light is caught by a CCD or charged couple device and turned from the analog signal, which is the light, into a digital signal. And that digital signal is given an algorithm, the algorithm that is used is what we choose on our screen. So whether we choose an AP chest, AP sacrum, PA chest, whatever, it's going to use the algorithm that's been programmed in by the manufacturer and apply it to that digital signal.
There are two different types of scans you need to remember. Now, I had mentioned the fast scan.
And the fast scan deals directly with the laser and how it scans the imaging plate. The slow scan deals specifically with the imaging plate as it goes through the reader, and that's also known as translation or subscan. So that slow scan is the translation of the imaging plate through the reader.
With the laser, it has to have constant
Power so that you don't get gaps or missing samples of information. And then, of course, the laser passes through a beam shaping device, and then it hits a mirror. And that mirror is kind of at an angle, and as the laser beam hits it, so it gets shaped, hits the beam, hits the mirror, and then comes down, the optical mirror is basically directing that laser towards the imaging plate. I'm going to change my color. Okay. So the laser beam directs it, or the optical mirror directs the laser beam towards the imaging plate.
things about the laser. It's usually a helium laser. There are some solid state lasers. It just depends on the manufacturer. But what you would need to know is the helium is the most common, and it is given at a wavelength of 633 nanometers. The solid state lasers have a different wavelength, but the helium ones, it's 633 nanometers as a wavelength. When the laser is scanning the imaging plate, it scans it in a zigzag or raster pattern. So it's like back and forth. Oh, that's not a good representation. So it's back and forth and back and forth and back and forth. And that's the raster pattern. There are different energies. So the laser light itself is emitted
at 2 electron volts. And when it stimulates the electrons to give off their light when they're trapped in that active layer or that phosphor layer that we talked about, the electrons emit a blue light, and that blue light is done at 3 electron volts.
And remember how I
said the laser stimulates the electrons in the phosphor center of that active layer or phosphor layer, and then it emits light. Those electrons get excited and emit light. The light is caught by the charge couple device or the CCD, and that light is turned into a digital signal. So everything starts off as analog, and then it becomes a digital signal, and it is given a numeric value.
That digital signal, it gets applied the mathematical
algorithm for that specific body part, and then it is being able to be displayed on our screens in our image matrix. Very important about our displays. Now that we know we've already taken the image, we've gone through the phosphors, we've gone through the plate construction, we did the reader, and now this is the display portion. It's very important that we have really good spatial resolution from the images that we're taking. And spatial resolution is the ability to see that fine detail, right? So spatial resolution is for detail. There's also contrast resolution, but contrast resolution deals with the ability to see 2 adjacent tissues or structures and their different gray levels. But spatial resolution is really where we get to see that nice detail. Obviously, the more line pairs we have per millimeter displayed, the better that resolution is going to be.
Now we've seen the image. We're going to post-process it as best we can. And then we are also going to try to get all the residual
energy out of the plate. So we want to make sure that we erase it. And in order to erase it, we do know that light stimulates the electrons, has them give off their own light, and then they come back to ground state. Well, we need to make sure that we can get as much of that electron energy out as possible, so we stimulate the electrons again by flooding it with a huge light source. And as we flood it with the light source, the electrons get all excited and give off a burst of energy and then come back to ground state. Now again, we never fully lose all of the energy from the stored electrons, but we do lose most of it. So we have to flood it with a huge light source in order for it to completely erase. So this is kind of demonstrating that here. Here's your big light source, and it's flooding it with all these light rays, and then it stimulates this phosphor layer here, and it's able to give off as much signal or as much stored energy as possible. Now we can process. We look on the screen, we're saying, hey, it looks okay, the EXI is good, and this is where we can look at the image, we can change things around, and then we can send it off to our PACS system. Here is just making sure that we've chosen the correct body part. You always should choose the correct body part so that the proper algorithm is applied to your image. You want to make sure that you're not trying to cheat the system by picking a different body part in order to get the proper S value or EXI number. You want it to be the right body part because you want to be as honest and ethical as possible when imaging patients. With digital imaging, it's a little bit different than our traditional film screen imaging where KVP controlled contrast and MAS controlled density. With digital imaging, KVP truly only controls the penetrability of the beam. Contrast is actually now controlled by the computer system itself. So KVP is strictly a penetrability technical factor. Your MAS is still dealing with the quantity, so how many electrons are boiled off from the cathode and sent across the tube. CR and DR systems, or your PSPs, are very sensitive to the quantity or the MAS used. If there is not enough quantity given across the tube so that you get enough photons in your primary beam, you're going to get graininess on your image or something called quantum model. So it looks like that snow that shows up on your TV if you lose signal. So not enough quantity or not enough MAS, you're going to get graininess or quantum model. Your KVP is just for penetrability purposes, and your contrast is controlled by your computer. Okay, make sure you get all those down. So our KVP values generally are between 45 and 120, but what's unique about PSP is that K edge, or that K binding energy for the phosphors or the barium fluorohalide family that we talked about. So we're used to having tungsten and that being a binding energy of 69 keV for that K shell. But when we talk about the K edge for PSPs, we're talking about the K shell or the K binding energy for the phosphor that's in the plate. And that binding energy is anywhere between 30 to 50 kiloelectron volts. Say that again. The K edge for the phosphors inside the PSPs are between 30 and 50 keV. And this slide is just basically saying that contrast is no longer controlled by KVP and that the contrast is determined by computer processing. MAS, same thing. Not enough MAS, you're going to get graininess, quantum model, or quantum noise. And this picture kind of shows you that. You can see all the little grains there. It looks snowy. Probably the last portion of Chapter 5 deals with grids, which I know you have been introduced to before. Grids clean up scatter, they make it look pretty, and we do use grids for thicker body parts. The main things to remember with grids are their frequency, their ratio, and the focus, meaning what SID they need to be used at. Is you want to make sure that if you have an oscillating grid, meaning a grid that moves back and forth to clean up scatter, that you don't end up with these lines here. These lines are called the Moiré pattern, and that's because the grid or the oscillating grid has not moved, so you end up seeing the grid lines. So these are just really grid lines that you're seeing on this image.
And here it talks about oscillating or the moving grid.
Grid frequency, you will not have to do a mathematical equation on this particular quiz for grid frequency, but you need to know what it is. So it's the amount of lines or lead strips per unit length or per centimeter or inch. When I talk about unit length, I just mean about literally a unit of length. So a centimeter, an inch, and it's how many lead lines per unit length. And that will give you your grid frequency. Your grid ratio is the relationship between the height of those lead strips and the distance between them. So it looks like H divided by D. So the grid, if that gives me a funny line, I'm going to be mad. Grid ratio. Ugh, I need to get a screen pen. Okay, anyway. So grid ratio equals the height of the lead strips divided by the distance between them. So you are going to need to know that. You will have to do it mathematically on the final, but for now you just need to know the definition of it. Grid focus, I had mentioned, talks about the specific SID. I can't see my mousey. Where's my mousey being weird? Aw, it's in pen. Highlighter. There we go. Sorry. Focus grids deal with specific SIDs, and it deals with the divergence of the beam. So those lead strips are in an angle that match the divergence of the beam depending on what SID it's at. So that's why in the departments you've got the pink ones that are usually for 40 SID and the blue ones which are for 72 because it matches the divergence of the beam. It's super duper important that you center appropriately for these focus grids. Parallel grids you don't have to center as much, but with focus grids it is very critical that you center the beam appropriately. Collimation, we know, is collimating down to the area of interest that we want to take a picture of. If we collimate down, we are increasing our contrast resolution because a lot of that scatter is being taken out of the image. So we're able to have better contrast resolution when we cone down. That's why if I'm working with you on the floor and you're doing an L5S1 spot, I want to make sure that you collimate down so we get really nice image contrast. Shuttering is a lot like collimation, but with shuttering it happens post-exposure. So it deals with post-processing. It happens after. So shuttering is not going to change the dose given to the patient. What it's going to do is remove that white space that goes around your image so that it looks pretty for the doctor. So this is a post-processing effect. You do it afterwards and you close it off so it looks nice for the doctor. It's not going to change any of the radiation given to the patient because the image has already been taken. Finally, the last few things I want you to remember are the certain artifacts that can occur on the images. Some of them can happen from the plate themselves, some of them from the reader, how we process it, printers. The artifacts that I want you to remember is as the plate goes through the machine and gets read, it's constantly taken in and out of the case, and as it gets taken in and out of the case, cracks can occur, and those cracks show up on our images as like fracture marks or fracture lines, so we want to make sure that the plates are in good condition. They look worn out. You can have artifact backscatter lines depending on how old the imaging plate is. Reader artifacts, most often you're going to get, and it uses a big word, extraneous line patterns, and that's caused by problems in the electronics of the plate reader, so it's not working appropriately. Sometimes the rollers aren't working right, but it's a huge line pattern. They're called extraneous line patterns, and this is what they look like. So something's not jiving right here, okay? That's it, and my office light just turned off, so that means I have to go. But I wanted to make sure this video was up and ready for you guys. I think you're going to be fine. If you have any questions, let me know. But, oh, no, discard. But this should be fine. I think you're going to do good. Deep breaths, study with each other, make those charts so that you remember the specific numbers for everything, and you'll be okay. Just review and don't overthink anything. Everything I talked about, everything in the PowerPoint I just put up is specifically for the test. You will be okay. All right? Take care and let me know if you need anything. Thanks.